All right, everyone, welcome to our first content lesson of our semester, where we're starting off with the big questions. What is science? And then specifically, what is earth science? So as I said in our introductory lecture, that earth science is the specific discipline through which I'm approaching teaching this course. So we're going to look at the big question of science and the question within that of the specific subdiscipline of earth science. And to be more specific about our lesson goals, by the end of this, you should be able to describe the common characteristics of scientific inquiry, identify the questions that are examined by earth scientists, and explain why knowing about earth science is useful for everyone. So to get us started, I just want to give you a question to think about a little bit. So imagine that you met someone who told you that they believed that the earth is flat. Right? They are a committed flat earther. How would you go about demonstrating whether or not they were correct, whether the earth was flat or, as I'm presuming, all of you out there believe that the earth is round? How would you go about trying to demonstrate that in a convincing and reliable way? You can pause the video if you want to think about that a little bit. So the first question that I would ask in approaching this is, well, why does it matter what we think about the shape of the earth in the first place? Why is this a question we're arguing about? Why do I need to prove to someone that the earth is actually round? Why do they care so much about insisting that it's flat? So that leads us to, I think, an important psychological point that helps us frame what we're doing when we're doing science, which is to think about, well, why do we believe things? Why do we believe something about the world or believe something else about the world? And fundamentally, the reason that we believe things is because our beliefs are useful. It's useful to us to hold a certain belief about the world. And there are some different ways that our beliefs can be useful, different uses our beliefs can have for us. So one category of usefulness is psychological. So a belief that's psychologically useful helps you feel grounded or fulfilled or valued or secure, right? It's a belief that makes you feel good to hold psychologically. And the meme that I've got there, right? It says paleontologists have agreed to start saying stegosauruses had beautiful singing voices because it's a nice thought and it's not like they're hurting anyone. What's happening in that meme is choosing a belief because it's psychologically useful, right? It's a nice thought to think this. But that's clearly a joke, right? That what makes this a funny meme is that we know that's not what scientists normally do. Right? If scientists are proposing to hold a belief because it's psychologically useful to them, they're probably not doing good science, right? That's not what we expect scientists to do. That's the humor of that meme. So while many people hold many beliefs on the basis of their psychological usefulness, that's not what we're interested in the context of science. Another way that a belief might be useful is it might be useful socially. It might be a belief that holding it helps us get along with other people and coordinate our lives with them. And research has actually shown that quite a lot of the beliefs that people hold, especially on controversial issues, they hold because of the social group that they're in, because holding that belief helps them to get along with people in their social group. So if you think, for example, about the question of, do you believe that evolution or young earth creationism is the best explanation for how we got all of the species of organisms that we have today? Most people hold a belief on that question that's based on what social group they're part of. So if you are a member of a fundamentalist, biblical, literalist church, that's your main social circle, you hang out with people from that church, and so forth, then it's going to be really hard socially for you to go around believing in evolution, right? That's going to get you weird looks and distrust from the other members of your church. You're going to feel like maybe there's something wrong with you. Why don't I believe this thing that all these other people that I know and trust and like and, share all my other beliefs with, is there something wrong with me for not believing what they believe about the origin of species? And so that's going to put social pressure on you to change your belief and to adopt young earth creationism to fit in with that group of people. And then the exact opposite, or Complementary thing would happen if your main social group, say, is people that hang out at an LGBTQ community center, right? That's a group of people that generally is not going to believe in young earth creationism. And so if you are hanging out at the community center with that crowd of people and you tell them that you are a young earth creationist, you're going to get some weird looks at best. And you're going to face that same kind of social pressure, that to fit in with these people, to get along, to feel good about yourself, and for them to like you and include you. There's going to be a lot of pressure to change your belief about the origin of species and to adhere to the theory of evolution. So that's how beliefs can be useful socially. And a lot of people hold a lot of beliefs because they're socially useful. But again, if we heard that someone was a scientist and was promoting certain beliefs specifically because they're socially useful, I think we'd have some questions. I think we'd feel like there's something wrong here. That person's probably not really doing good science if they are actively basing their beliefs on what's socially useful. So that brings us to the third category of ways that beliefs can be useful. Beliefs could be practically useful. They are beliefs that help us successfully interact with the external world. So there's all kinds of stuff we want to do that involves interacting with the world around us. And in order to interact successfully, we need to believe certain things about the world. And some beliefs will lead us to success, some beliefs will not. So if I have a pot on the stove and I have the belief that that pot is really hot, then that's going to lead me to do things like not touch it because I believe that it's hot and would hurt my hand. It also may lead me to put my pasta in that pot because if I believe it's hot, then I believe that it can cook my pasta. And so then I may find that I have successfully interacted with that piece of the external world because I've avoided burning my hand and I've got my pasta to eat because I held the belief that that pot was hot. If I held the belief that a pot was hot in a different context, then maybe I wouldn't successfully interact with the world, right? I might put pasta in the pot and sit there and then, I get it out and it's still crunchy. And so in that case, a belief that that pot was hot didn't lead me to a successful interaction with the external world. And it's this practical usefulness that is what science is trying to help us with. We can think of science as a way to systematically generate beliefs that are going to be practically useful, beliefs that are going to help us successfully interact with the world that we live in. So to be more specific, right, what kinds of things do we want to know about the world, or beliefs do we want to hold about the world that will help us successfully interact with it? We can think of scientists aiming at doing 4 different things. These are sort of 4 levels of things that we can believe about the external world that help us to interact successfully with it. And to illustrate them, I'm using the example of a hurricane. Okay, so if the hurricane is kind of our topic, what might we try to know about that hurricane? So we might start with the goal of description. We want to describe that hurricane. We want to be able to say, how big is it? How fast are the winds blowing? Where is it moving currently? What kind of precipitation is happening in it? What's the barometric pressure at the center of it, right? These are all descriptions of the hurricane. They're information about what it is and what it's doing. Once we have a description, we can then move on to explanation. So explanation is asking why. Okay, so we have a hurricane, we can describe it. Why do we have a hurricane? Why is there a hurricane right now of this particular size moving over this part of the ocean with this, speed of winds in it? And why is there not a hurricane, over here? A different part of the ocean has no hurricane in it. So why is there a hurricane with these characteristics here? Why is there no hurricane over there? That's explanation. That's the why questions. Then if we have good explanation, we might be able to move on to prediction. We have a really clear explanation of why a hurricane forms in the way it does, at the place it does, at the time it does. We can predict where that hurricane is going to go, what its effects are going to be. And of course, we see that if you follow the news during hurricane season, you see a lot of effort put into that prediction, trying to guess or not guess, trying to have something better than a guess, where that hurricane is going to go, what places it's going to hit, which people therefore need to be worried about it, need to maybe evacuate, or nail boards over their windows or whatever else they might do. So we want to be able to predict what's going to happen with that hurricane. And then the highest goal that we might strive for is control. So if we can describe a phenomenon, if we can explain why it works, if we can predict what it's going to do, we might be able to use that knowledge to control that phenomenon in some way. And so with a hurricane, like the ultimate form of control would be if we could make hurricanes appear and disappear at will, right? And that might be pretty handy. If you're in a city that has a hurricane bearing down on you, it might be nice if someone had the ability to go in and neutralize that hurricane so you don't get hit. We're nowhere near that right now, right? That is a level of control that we do not have in the field of hurricane science. But there are things that we can control. So we might look at how can we reduce the damage that that hurricane is going to do. So we can't control the hurricane's winds, but we can control, the houses that the hurricane is going to hit, and maybe do something different to make those houses more resistant so that the hurricane doesn't destroy them. We can move people out of the way so that they don't get tossed around in the winds or drowned in a flood or something. There are various things we can control about the hurricane, even if we can't completely control the hurricane itself. So scientific inquiry on different topics may be at different levels, right? Some scientific topics, we're still just struggling to describe what's out there. Others, we have pretty sophisticated control over certain systems that we have knowledge of. Other things are in between. But these are some of the kinds of things that a scientific inquiry might be aiming at trying to do. And all of these will help us to more successfully interact with the world around us. They will help us to do things like, in the hurricane case, avoid getting killed by the hurricane. So if we're going to try to systematically generate these practically useful beliefs, and we're going to use the scientific process to do that, there are certain premises that we're going to make use of. There are certain things that we are going to use as the basis for investigating the world. And these are premises that help us distinguish science from things that are not science. And things that are not science are not necessarily, invalid, bad, wrong. They're just not science. They're a different form of knowledge that you might hold to. So some of the key premises of scientific inquiry I've got listed out on this chart. So the very first one there is a real world external to us. Science is about generating useful beliefs about an external world. So if you think that the world is all an illusion, we're all just living in a dream, or everything in the world is a social construct and there's no objective external things out there, you're not going to get very far with science. Now, science isn't going to be able to generate useful beliefs about that external world if you're starting from the premise that that external world doesn't exist. Another premise of science is that phenomena follow consistent rules. So science approaches knowing about the world by looking for patterns, by looking for consistencies to say, oh, when we get X, we always get Y after that. That's a consistent relationship. And so that means if in the future we see X, we know that Y is coming. So we're looking for consistent rules on which that external world operates, and that helps us form these useful beliefs. So if you believe that phenomena have unique or one-time causes, then science isn't going to be able to get a grip on those things. So miracles, for example, right? A miracle is where the pattern of how things work is not followed. God directly intervenes and does things differently than it's ever happened before and never will happen again. Science can't tell you anything about miracles because science needs these consistent patterns of how phenomena work in order to figure these things out. Science also has the premise that the universe is knowable, that we can have useful knowledge about the world, that a thing that we set out to inquire about, there are answers that can be obtained. Now, of course, there may be practical limits on what things we can know at a given point in time. Right? There may be experiments that we simply don't have the ability, we don't have the time, we don't have the resources, we don't have the power to conduct but in theory we could, right? So the universe is only unknowable because of our human limitations in that case. But a non-scientific worldview might hold that there are certain things that are inherently unknowable. And so if there are things that are inherently unknowable, science can't tell you anything about them, right? Science can't get to grips with that. That would also apply if certain things are morally unknowable, like it's wrong to know certain things. Scientists want to know things. They want to investigate anything that can be investigated. So if there are certain categories of knowledge, certain topics of knowledge that are wrong to know about, then that would be outside the domain of science. Science wouldn't be able to do anything about that. Another important premise of science is that nothing is self-evident. We want to be able to question everything. We want to be able to look at our understanding of the world and say, wait a minute, have we ever really investigated that thing? We should check that out, make sure that it's actually right, rather than just assuming that it's true. Because lots of things that appear self-evident, that appear to be, that we could just take them for granted about the world, actually turn out under investigation not to be true. So if you have a solid object, right? I happen to have a comb sitting here next to me. I don't know how well you can see it on the little video there, right? But when I look at this comb, it seems like it is made completely of material. There are no voids in this comb unless I broke a tooth out of it. Right? This comb is all stuff. But in fact, scientific investigation has shown that this comb, like any other physical object, is over 99% empty space. Right? That's an extremely counterintuitive idea. This comb certainly doesn't seem like it's 99% empty space. I can, hit it and it seems really solid. How is that 99% empty space? So if I were just taking for granted that, well, intuitively, obviously, this comb is solid and complete with material, then I would be making an assumption that doesn't hold up and that turns out not to be very useful. That might be a perfectly useful thing to assume in everyday life when I'm combing my hair or whatever. It might not affect anything. But there may be other scenarios. If you're a comb engineer designing better materials for combs, you may need to know that at the molecular level, this comb is, and all other materials in the world, is 99% empty space. So scientists don't take anything for granted. We try to question everything and make sure that it's really true, rather than assuming that we can know certain things, intuitively, or some things are just so obvious that we don't need to check them. And then the last premise that I've got listed here is that knowledge comes through observations made through our senses. So ultimately, all of the claims we make about the world in a scientific context should be grounded in observations that we make with our five senses, or more than that. The five senses model is actually a little outdated in terms of how they slice things up these days. But we should base it on what we can see, either directly or by watching how an instrument measures things we can hear, things we can touch. Right? All of that is the basic data on which we should be building our beliefs about the world. Whereas in a non-scientific context, someone might say that valid knowledge can be based in something like a divine revelation, or on knowledge that comes in a dream, or something like that. Right? Those are things that many people take as bases for beliefs about the world. Right? I dreamed about X, therefore X must be true about the world. But if you're doing that, you're not doing science. Right? Science needs to be able to base everything on sense observations about the world. Now, on this slide, I've got labeled tendencies of scientific inquiry. So the previous slide are things that are pretty much always going to be true about science. If you're not doing what's on that list, probably not doing science. This slide is things that are commonly found in science, that science tends to do, but that aren't quite as definitive, that you can find examples of science in good standing that might not have one or more of these tendencies, but these are things that we usually expect to see from science, and we usually would want a good reason why a scientist was deviating from these tendencies. So the first one is that science tends to use quantitative thinking. This means we describe things in terms of numbers. So if we're looking at that hurricane from a few slides ago, we don't want to just say there are a lot of fast winds. We want to be able to say exactly how many kilometers per hour are those winds blowing at each different part of the hurricane. We don't want to just say that, oh, it's hitting South Carolina. We want to be able to say, well, it's hitting exactly between this latitude and that latitude. We want to be able to put numbers to things in science. We have quantitative thinking. Qualitative thinking, where we describe things without using numbers, tends to be found in non-science. Okay? And so probably many of you are in majors where you don't use numbers a lot, right? If you are, for example, an English major, right, you describe a lot of things when you're analyzing a novel without using numbers. I know there's quantitative humanities studies and stuff out there, but probably most of the time you're analyzing a novel or a poem or something, you're not doing it in numerical terms. You're not trying to put numbers to what the author is doing. You are doing a qualitative analysis, and that is a totally valid mode of inquiry, but it's a humanities inquiry. It's not a science inquiry. Another tendency of science is to generate theories that are falsifiable, which means that there's a way that they could be proven wrong. And the way that you support your theory is by trying to prove it wrong and failing. By saying, here's what my theory says, here's what would be inconsistent with my theory. I've gone and looked to see if we can find anything inconsistent with my theory, and I have failed to do so. Whereas if your theory is non-falsifiable, if it's a theory that would remain true regardless of what the results of an investigation or an experiment would be, then you're doing non-science. So if we refer all the way back to the question that I posed about the flat Earth, there was recently a group of people that attempted to falsify different models of how the Earth is shaped. So on a globe Earth, we would expect that you could get 24 hours of sunlight close to the South Pole, because as the Earth is rotating, its axis is tilted, and so during the southern hemisphere summer, the southern hemisphere is tilted in towards the sun, and so at a high enough latitude, the sun will stay above the horizon for at least 24 hours, sometimes much longer than that if you're close enough to the pole. On the most popular flat Earth model, which is the one that was on that slide, they imagine the Earth is a flat disk with Antarctica as an ice wall around the outside, and the sun makes kind of a little circle above the Earth, and kind of like a spotlight just lights up part of the Earth. So on that model, you couldn't get 24 hours of sun in Antarctica. It's out at the edge there, and so only part of it can be in the spotlight at one time. And so a group of people, a mixture of flat earthers and people who are critics of flat earthers, went down to Antarctica and observed the 24-hour sun. Some of the flat earthers said, okay, I have seen evidence. It has falsified my theory. My theory, the Earth is flat and the sun makes a little circle around it. I've now seen evidence that contradicts that theory. It's falsified my theory. My theory can't be right. And so they've changed their view about the shape of the Earth. Other flat earthers said, okay, sure, we saw a 24-hour sun down there, but we're not going to throw out our flat Earth theory. We're going to come up with a way that you could actually see 24 hours of sun in Antarctica under a flat Earth model. So their theory was non-falsifiable. If they had not seen a 24-hour sun, they would have said, aha, theory is correct. They saw the 24-hour sun. They still said, aha, our theory is correct. Their theory was not falsifiable. They were able to massage the theory to account for whichever result they got. So the flat earthers who changed their view after seeing the 24-hour sun were approaching things scientifically. The ones that did not change their view after seeing the 24-hour sun were not approaching it scientifically. They had a non-falsifiable theory about the shape of the Earth. Another tendency of science is to look for the simplest adequate explanation. So the simplest adequate explanation might still be really complicated, right? Because a simpler explanation of something wouldn't account for all the data. And so you may need to make it pretty complicated to account for all the data. But given a choice between a simpler explanation and a more complicated explanation that both adequately explain the same data, science prefers the simpler explanation. On the other hand, if you are embracing complexity for its own sake, and you want a complex theory of the world just because it's cool to have a really complicated theory of the world, then you're probably not doing science, right? If you're embracing the complexity for its own sake, not because you need the complexity to fully account for all of your data. Science also generally thinks in terms of forward causality. So your cause precedes your effect in time. Cause happens first, effect happens after that. So things that happen in the future can't affect the past. On the other hand, if you're creating a theory about the world that implies, say, backwards causality, that what happens in the future affects the past, that what's happening now is because of something that's going to happen in the future, you're probably not doing science. And here I emphasize that probably because there are some interesting questions about the possibility of some form of backwards causality in certain theories that scientists have generated about quantum dynamics, the way that the very tiniest particles interact. And that's not, settled science. That's kind of the cutting edge of particle physics. But that's why I say put this on the tendencies page, the tendencies slide, not the characteristics slide. So generally speaking, scientists are going to look for forward causality. The cause comes first, and then the effect comes after. And then the last tendency that I've got listed here is that science tends to be analytic. Science tends to approach understanding things by breaking them down into their smallest parts and then seeing how the parts fit together to build up the whole. Okay, so you break things down into the smallest parts and then build back up from the interactions of the smallest parts. On the other hand, if you are thinking holistically, if you are saying the whole is greater than the sum of its parts, the whole can't be understood as the result of the interaction of its parts, then you're less likely to be doing science. And I put that one on the bottom of the chart here because that's probably the weakest of these tendencies. And in particular, within earth science, we very often will find people saying that a holistic view is actually helpful and falls within the bounds of science. So science in general is more likely to be analytic than to be holistic. So that's a tendency, but it's not a sharp dividing line. Excuse me. Okay, so you're going to be encountering a lot of stuff in this course and, of course, in your life outside of this course that claims to be science. And one of the things that I hope that you get out of this course, one of the skills that I hope you develop, is the ability to recognize good science. To recognize when is something that someone is saying is scientific good science, when is it bad science or not science. And so I've got some questions there that are good questions to ask whenever you encounter something that claims to be science. And you want to evaluate it and decide if you should treat it as good science. So first, who is saying this? If someone is saying science says X, who are they? What are their qualifications and experience? So that's part of why I laid out a little bit of my biography at the very beginning of this class. I want you to know who I am, where I'm coming from, why I have any authority to tell you things about science. Okay, so what are this person's qualifications, experience, that may be formal qualifications, having a PhD or something. There could be good qualifications and experiences someone has that are very relevant to the thing they're talking about that might not be formal university qualifications, degrees and stuff. But you want to look what's the grounds that this person has for speaking on this. And also, do they have conflicts of interest? Right? Are they being paid by a company that would benefit from people believing a certain thing? Well, then they might have a conflict of interest. They might be telling you certain things because it's, helps out their bottom line rather than because it's really the best scientific information. It's really the thing that is going to give us the best ability to practically interact with the world. Then you also want to ask, what are their sources? So where are they getting this information from? Right? Are they citing research that has been conducted and peer reviewed? Are they citing their own data that they've collected? And if so, how did they collect that data? Where are they getting the information from? And can you trace that information back and kind of double check that they are representing it correctly? Third, do other sources agree? So in science, we usually don't have one person who has their one idea and they did one study and now we're like, all right, cool, we've solved it. We do many, many studies and we look for useful information to emerge from the agreement of many people doing many studies on related topics. So you want to look, one person is telling you one thing in science. Does that agree with what other sources say? And why or why not? Because it may be that there's a flaw with all those other studies. And this is the person that has figured out that flaw. And so there's an explanation of why they're the only one saying this right now. So this is not to say that you always have to go with whoever has kind of the largest vote behind them, the largest number of sources. But you should have an explanation of why the science that you are going to believe in gets a certain result if there are other sources that disagree. Right? You should have an explanation of why you're siding with one rather than another. And through all this, I think it's important to think in terms of better or worse rather than good or bad. So we don't have a simple dividing line that says there's science, good science here, and there's bad science here, and it's either right or it's wrong. Rather, we have things that can be better, things that can be worse. And so you want to try to move towards the better science, move away from the worse science, but you don't always have the perfect information. And sometimes you need to make a decision. You need to do something with this information, right? You need to act on it and hopefully interact successfully with the external world when you don't have perfect science to work with. So you want to think in terms of better or worse rather than good and bad as like a dichotomy. Okay, so that's science in general. What about earth science, the specific form of science that we're going to be looking at in this course? So earth science, which is also known as geoscience, is the study of the processes that shape the earth. And within that wider umbrella of earth science, we have subdisciplines like geology, hydrology, meteorology, climatology, ecology. And the picture there, if you note the caption, that is actually a group of Slippery Rock students who went on a big field trip a few years ago with Dr. Burkhart to the Badlands of South Dakota, and they're doing some science. They're recording their observations there of the processes that formed those really cool dramatic cliffs that you see in front of them. So in this particular case, these students are working in the subfield of geology. So to explain a little more about what these are, geology is the portion of earth science that deals with the solid earth beneath us, the rocks, the minerals, the soils, the solid parts of the earth. And so as an example of a question that a geologist might examine, I've got, how can lithium be extracted from low concentration ores? So lithium, useful mineral, especially now as we're shifting into a lot of the green low carbon technology. We need lithium for batteries and things. So geologists might try to examine how can we extract lithium from ores where there's a low concentration of it, because it's become such a valuable mineral that requires understanding the chemical and physical structure of those ores, how they're formed, where they're located, etc., to be able to answer a question like that. Hydrology is the subdiscipline that deals with water. Water systems on the earth are studied by hydrologists. And so my example inquiry that a hydrologist might do might be to answer the question, will adopting permeable paving materials reduce flash flood events? So there is paving material that is being produced these days that water can actually seep down through. So rather than the water just running off the top of the pavement into the ditch or the drain, it will seep down through the pavement into the soil below. And the promise of that, the reason that those things have been invented is because we think that might help to reduce flash floods. If that water gets absorbed into that soil rather than just running off all at once into the stream, we won't get that sudden flood. But that's the theory. Does it actually work? if we paved an area with this permeable paving and we have, comparable areas that have traditional sealed off paving, does it actually help enough to be worth the extra cost of installing this new paving material? So that's the kind of thing a hydrologist might be interested in. Meteorology is the study of weather, the short-term patterns in our atmosphere, the air on our Earth. And so meteorologists are interested in hurricanes that have been one of our examples in this lesson. So they might ask things about, can we improve communication of hurricane warnings to the public? That's one of our ways of controlling the impact of a hurricane, is to warn people so that they can take precautionary measures, they can get out of the way, they can secure their belongings, etc. And so can we better predict how those hurricanes are moving and who we need to send those warnings to in order to improve the outcomes of a hurricane hitting an area. Then we have climatology, which is the study of climate, the long-term patterns of our atmosphere. And so a big topic that climatologists spend a lot of time on these days is climate change. So the alterations to the Earth's climate that are happening right now, largely due to human activities. And so a climatologist might investigate a question like, how will climate warming affect cloud formation? So we know that the Earth is getting warmer, right? Our climate is becoming warmer, but how will that affect the formation of clouds? Will we get more clouds in a warmer world? Will we get fewer clouds? Will we get different kinds of clouds? And then what are the ramifications of that for things like rainfall patterns in different parts of the world? So that's the kind of thing that a climatologist might look into. And then ecology examines the interactions of living organisms with each other and with the non-living parts of our Earth, with the water and the atmosphere and the rocks and landscape and so forth. And so the interactions among all those things and with living organisms is ecology. So an ecologist might be interested in wildfire, right? Because it's burning through some of those living organisms. And so an ecologist might ask, what effect would restoring indigenous fire practices have on endangered species? Maybe we have some endangered species living in a certain area, and if we shifted from the current system where we try to extinguish every fire as soon as possible, and so you never get fires burning through this forest, and we shifted to something more like the indigenous fire practices that were going on, 200, 300 years ago, where they would light fires on a certain rotation, smaller fires within the ecosystem, would that help these particular endangered species that we're interested in? So these are the kinds of inquiries that earth scientists might be doing. And in this course, we're going to touch on all of these different subfields. So you're going to learn a bit about geology, a bit about hydrology, a bit about meteorology and climatology and ecology. What's going to tie it all together? I have a slide before I get to that. So why is this useful? Why should we learn about earth science in the first place? Well, I think the fundamental reason is because the Earth is our home. The Earth is the only planet that humans are able to live on. The tiny handful of people that have ever left the Earth and gone into orbit or gone all the way to the moon were still dependent on the Earth. They were still eating food and drinking water that they had brought from the Earth. They could not stay out there indefinitely. So the Earth is the home of all humans. So all humans should know something about the Earth and how it works. Everything we do depends on the Earth. And at the same time, we're also part of the Earth. So all of these Earth processes that we're going to be learning about, we're part of that. The atmosphere runs through our bodies every time that we breathe in and out. The climate system affects how we live. Water flows, you're made mostly out of water. So we're not only living on Earth, but we're part of Earth. We're part of these processes that shape how the Earth works. And we also have a responsibility to be good stewards of the Earth. And so this is something that you can find in pretty much any religion or ethical system out there. Will say that in some way we have a responsibility to be good stewards of the Earth. even if purely for selfish reasons, because we don't want to suffer the consequences of what might happen if we don't take good care of the earth. Other religions or philosophies might have a much more expanded idea of, what our responsibilities are. But, in whatever system you subscribe to, you have some sort of responsibility to take care of the earth and the conditions that it provides for our continued existence. And within this, there's going to be lots of room for political and ethical debate, because my political and ethical system might not be the same as the one that you subscribe to, and debating the details of that is outside of the parameters of this class. But we should be able to have that debate if we're going to have it as like fellow citizens deciding what to do in our world. We should be able to have that debate in a way that's informed by good science about how the earth actually works. So if one person is arguing in favor of, say, a carbon tax that would reduce CO2 emissions, and another person's arguing against implementing that carbon tax, it's going to be a lot better if both of those people understand the relationship between the emissions and the carbon change. And so then they can argue about, is that trade-off worth it, right? Is the cost of that carbon tax worth the gains in reductions in emissions or not? Rather than an argument where one of those people denies that emissions are causing climate change at all, and the other person is sort of a panicked catastrophist that thinks that everything is going to be destroyed if we have just a little bit more emissions, right? Neither of those are scientifically grounded beliefs. But if we can agree on what science says are the beliefs that will lead us to the most successful interactions with the world, then we can debate the ethical and political questions of what kind of interactions do we want to do. Okay, so for this class, our particular focus is going to be on natural hazards. So that is going to be the through line that's going to connect all of our different looks into different aspects of earth science. So we're gonna approach those different subfields of earth science through the question of natural hazards. And we're going to look at a variety of different kinds of natural hazards. We're going to look at volcanoes, and earthquakes, and flooding, and erosion, and wildfire, and sea level rise, and storms. So we're going to look at all these different kinds of natural hazards, and we're going to be asking, why do they occur? Okay? Why does a flood happen in the kind of places that it happens in, at the frequency it happens? Why do wildfires happen where they do and have the effects that they do? We're going to ask, what are their effects? So what happens if you get flooded? What happens if there's an earthquake where you are? Now, what kind of effects should we expect to see from these kind of hazard events? And then how can we protect ourselves? So I want this to be a class where you're getting some practical information that you can apply in your life. So if we're learning about floods, well, that's a thing that might happen to you. As you're deciding where to live, you might think about, well, what happens if there's a flood here? How likely is it? What preparatory steps might it be worth it for me to take just in case there is a flood? What do I do once the flood has happened? Okay, so these questions about how we can protect ourselves in case of a natural hazard are going to be the important upshot. And that's what I'm going to try to lead us to in all of our lessons is, okay, well, what can you do with this information? How might this help you or affect the life that you live so that hopefully you aren't harmed by any of these natural hazard events? So that's what we're going to be doing for the remainder of our semester. So that's it for me for right now, and I will see you in the next lecture.